I'm very pleased that I have such a big crowd. I was thinking that there'd be 3 people after a long day on a Saturday at 5:30. It's an unimaginable time to be listening to more research. So thank you for coming. It's a privilege to be here and to give some thoughts about my research and our research in Edinburgh. And you probably are wondering what's so interesting about a system paper at a shared task in machine translation. So I was trying to motivate this talk a bit because firstly, I think it's quite an interesting piece of work. I'm quite proud of it. So okay, it's maybe not as groundbreaking and high level as, say, Fernando's talk was yesterday on paradigm shifts and attention models and stuff. But actually, yeah, it's a bit more prosaic. But I think that this paper is quite an interesting paper. It's also very good. I think it's good science. It'll give you a bit of an overview of the work that we're doing in Edinburgh on neural machine translation. So if you don't know anything about neural machine translation, you'll see a number of different things that we're trying. Also, I think it's an example where we've put a lot of effort into the paper. So we've trained up a lot of different systems on different language pairs. We've done ablation studies. So I think it's quite a good example of how I would like to see more papers, especially in neural machine translation. You know, strong baselines, and where you can actually be pretty convinced that the results are actually correct. So I think, especially if you're starting out in machine learning, that could be quite useful to maybe be shown an example of the kind of research that will get that will really convince your audiences of the points that you're trying to make. But I'd also like to make another point, which when I was starting out in machine translation, I didn't really realize, was that shared tasks and workshops are actually a really important part of certainly of machine translation, because that's where the community get together and they form a consensus on what is the generally accepted view of what works and what doesn't work. So, you know, potentially there might be a paper that comes out this year and it's very exciting, and, you know, they have a really novel idea and they show it on one language pair and they get some really good results, and then, you know, you never hear anything more about it. And so it's at the shared tasks. If something has been proposed and it really works, what you'll see is that people will reproduce this work, and because it's not glamorous reproducing work, it's hard to publish. Shared tasks are really the venue where you get to show that, yes, this piece of research actually did work across, you know, a broad range of tasks and language pairs. And then what happens is that kind of body of knowledge becomes shared and embedded, and then things can really progress the next year. So I hope I can encourage you to participate in shared tasks. This also, it was actually quite a big effort from my group, so you can see that there were 8 of us involved in doing all these experiments, and we did experiments across 12 language pairs, and each of the language pairs we trained up 8 separate individual models, so we used a lot of resources to do this study. Luckily, Kenneth Heathfield managed to get some time on some credits on Azure, and I think we spent about $30,000 on computing resources to run all of these studies and all of the ablation studies. So it is actually, I think, a valuable piece of work. I'd like to highlight that the big contribution made by my main collaborators, Rico Senrich and Barry Haddow. So I was looking at the schedule of the machine learning workshop summer school and noticed that you had quite a lot of detail about linear models. And I certainly spent about 10 years working on phrase-based machine translation, which is maybe the epitome of a linear model. There was hundreds of researchers working on phrase-based machine translation for nearly a decade, and an enormous amount of research went into making it better. But in essence, a log linear model is formally defined here. So the probability of a translation, T, is equal to a function which the log of which is a linear combination of different features. So here we have n is the number of features, x are the random variables, so e is the target sentence, the translation sentence, and f is the source sentence, and then start and end would be the start and end positions of different phrases in the translation process. And I've given 3 examples of feature functions here, the kind of classical 3 feature functions. So H1 is the translation probability, so the probability of the translation given the source. H2 is an example of a very basic distortion model. So here it's not actually a probability, it's just it defines a distance between the order of the phrase on the target compared to the order of the phrase on the source. So that would encode the ability of the model to prefer translations which are largely monotone. And this is more successful for some languages and less successful for others. And then the third feature is a probability model. It's a language model over the target sentence. And then we combine all of these features with lambda weights, which we have to learn. And learning lambda is a very difficult task. So to make it all a little bit more concrete, I put up here an example of a parallel sentence. Then this is the kind of data from which we learn these models. So we could have a source sentence such as, if caught early, the progress of the disease can be slowed down. And then we're trying to learn all the features, all the distributions of the different features, and then how we combine those features together as well. So, you know, in the general learning framework, we would break down the sentence into phrases. We would then learn the individual probability distributions of how we translate these phrases and how we reorder these phrases. And surprisingly, this model actually was the state of the art for pretty much a decade. And a couple of years ago now, neural models came on the scene, and it's a completely different kind of story, right? This model is one single mathematical function where all of those different features, all of those different decisions occur together inside. You know, this is a very, very high level view of it, of course, but you could imagine what you have basically is a source sentence here in German at the bottom that then gets represented in some way as vectors, could be potentially one-hot vectors or something of the like. And then the output of this mathematical function are probabilities which would allow us then to choose words in the target sentence and produce a translation. So from a very, very high level, we can see how different the previous kind of linear models were to what we're working with nowadays. In phrase-based statistical machine translation, we would learn segment-to-segment correspondences from the bytext. Training is this multi-stage pipeline of heuristics. People would actually, you know, try to invent new feature functions and then spent years testing to see if they worked, and ended up with, you know, first tens and then thousands of features. And then we have fixed weights for the features, so the lambdas are fixed, which is crazy. You know, you'd have a weight for a language model, and it would be, you know, 0.1, and it would be 0.1 for no matter which sentence, no matter which word you're producing. That language model always would be given the same weight, and that is clearly not a good thing. It had a limited ability to encode history, so we have language models which have some idea of history, but they've got a limited history because they have problems with estimating these probabilities. They have problems with data sparsity, and they also had they were also defined language models over translation, phrasal translation, so people could get some sort of idea of the history of what has been previously translated. But all of these things were independently combined. Well, they had weights, but more or less they were acting independently. They're trained more or less independently, and then stuck together. And so neural machine translation really has some fundamental improvements over phrase-based machine translation, where, you know, the single one mathematical function is now trained end to end. You know, no longer do we need to go off and create and estimate and define hundreds or thousands of features. And the other nice thing about neural machine translation is that we're actually able to encode theoretically unlimited context, although of course in reality it is limited, but we have far more context than we ever had before. And then, like a key advantage as well is that the weights of all these features, these features are no longer explicitly defined; they're now implicit in the model, and their weights and the features themselves are all emerged together. And because the model is highly nonlinear, different parts, different elements of this context and these sort of implicit features can be important at different points. So something that could maybe be equivalent to the language model on the target side could potentially be more important in some places than another when producing the translation. So although yesterday Fernando gave a description of some very exciting research which is questioning my statement and this slide in particular, how I was claiming that recurrent neural networks are fundamental to neural machine translation models, and that's maybe not true today. We now have transformers, thank you Google. But you see, that will only be accepted next year after the shared task in 2018. So we still have the jury's out. We still have to see if that's going to be adopted as the next standard. Exciting as it is. So recurrent neural networks. Here we have a very basic high-level diagram of it, where at position I, the hidden state I depends upon the input context, and then context from the previous hidden state I minus 1. And then from that we're able to produce the output yi. And recurrent neural networks are essentially fantastic ways of modeling sequences. So they're able to summarize a long sequence of input embeddings and encode some kind of summary of that sequence. And so for language modeling, they're perfect. So if we're trying to predict the next word, wi, we can actually condition on the entire history of the sentence since the beginning, w1 to wi minus 1. And these models, as we all know, outperform traditional n-gram models by a large margin. And then 4 years ago, there was the first work that came out in fully neural machine translation models by people such as Phil Blanson, where they suggested this architecture which was called the encoder-decoder architecture, where the intuition is that if we have a language model that is really good at producing sentences, why don't we condition it on a sentence in another language, and then we have a translation model. And we don't have to do much more. And this incredibly simple idea was kind of revolutionary at the time. You can't believe that we can do an entire end-to-end translation model just with a recurrent neural network language model. And it seemed to work pretty well, actually. For shorter sentences, you would get very fluent-sounding output sentences. But it tended to break down as soon as the sentence got a little bit longer or something was a bit more complex. Translations were really poor. It was a very unreliable model, very, very far behind phrase-based machine translation. And then Badenauer in 2014 proposed the encoder-decoder model with attention. And this is the last slide on the background to neural machine translation. But this model really defines most of the current state-of-the-art machine translation models, and has also been used very, very widely in natural language processing and other places for any kind of sequence-to-sequence tasks, such as summarization or even parsing. And so what we have here is the intuition is that in the previous encoder-decoder models, we were relying on this single fixed-sized context vector from the source sentence. And if it was a 3-word sentence, it was the same size. If it was a 30-word sentence, it was the same size. And we weren't able to encode all the context that we would like in this one context vector. So the attention model, what it allowed us to do was to actually pay attention to a combination of all the context from all the different words in the source sentence, and then to pay a different amount of attention to each word depending on the target word that we're producing. So in this case, we're producing S3, or we're predicting John, and the attention model is able to pay more attention to the word John in the source sentence than to the other words in the source sentence. But this model, even though it was a breakthrough, of course, we're still working on it, we're still improving it. A big problem with these models, of course, is that machine translation is a massively open vocabulary task. You could have 500,000 words in your training corpus and still have a lot of out-of-vocabulary words in your test. And the size of the vocabulary very much determines the size of the model. And anything over about 50,000 words in your vocabulary becomes quite problematic. Another limitation is that these models, there's an enormous number of parameters, and they take a really long time to train. So they can take between a few days if it's a small training corpora to like 2 or 3 weeks for the very large corpora that we use often. The other thing that we're noticing is that in other fields such as image, that people are using really much, much deeper models. And although we have recurrence and there's arguably deep in its own right, we could potentially add more layers and improve quality. And the other thing is that if you look at training and you're doing validation, you can see that the scores, the blur scores that we use to evaluate machine translation go up and down quite a bit. So it's not very stable. So in this year's workshop in machine translation, we were trying to address all of those problems. And some of these things we were reproducing from work done in the field, but we also produced some novel research here, and I'll talk about that now. So the first thing we addressed is we were trying to make models smaller, and that would allow us to make them bigger again. So last year in last year's WMT, last year's ACL, we proposed a method of dealing with large vocabulary in machine translation by translating over not words but over subword units. And that way we could have quite a limited vocabulary, say 50,000 words, but still cover any potential words in our test set. So a lot of work has been done on segmentation in NLP, but a lot of segmentation has been based on linguistic knowledge and training data to train morphological segmenters, and these are we did experiments with these, and we found a way that a method that actually works better and is completely language agnostic, and you can just apply out of the box to any target language that you want. And this is the idea of byte pair encoding. So the idea is that you start off with a vocabulary which just consists of characters, and then you iteratively combine characters to form two-word items in your vocabulary, and those when you merge them, what you're merging is the most frequent two-character sequences. And so what you see is that frequent words, such as the, very quickly become items in their own right in the vocabulary. The disadvantage is that you need a parameter to say when you're going to stop, so you need to say, I define my vocabulary to be, I'll do 50,000 mergers, and then you have a vocabulary of 50,000 plus the number of characters in your training set. But we also saw that if we did this jointly over, say we had English and German, if we did it separately, we'd end up with different segmentations for instance, for names or words that were similar in the two languages. And it was more consistent if we did this segmentation approach. We learned which mergers to perform and created our vocabularies together in a joint concatenated corpus. But there were some unintended side effects of this that weren't really great. So the main problem here was that sometimes a subword unit can be really frequent in the English, for instance. An example here, nationalities, but it's only been seen once in the German. It's very rare in the German. So if this happens, the model is unlikely to learn good representations for rare subwords. And we can even see unknown words occurring in our test corpus, which is what we were trying to avoid in the first place. Because if we'd seen this subword unit only in the German, and then somehow we have a test sentence, but we have this subword in the German, we might apply it to an English word in our test. And then this is now an previously unseen word coming in as test, and then we obviously will perform very badly on it. And then the final problem is that when we have rare subwords like this, it's actually quite wasteful in the vocabulary. So trying to improve on that, we came up with a new version of BPE, which is also available online if you want to use it. It's quite a widely used method now in machine translation and other fields, that we now require that a subword has been observed at least once in the source corpus, and we optionally require that the subwords are seen by some minimum frequency. So it's unfortunate to have now have another parameter defining minimum frequency, but we can see that if we set that threshold to 50 in our this table here, we can see the vocabulary size. And when we don't have this filter, and we allow 90,000 merge operations when training our BPE model, we end up with a vocabulary on the German side of 91,000. So this is the 90,000 items that fall out of the merge operations, plus 1,000 words from the individual characters in the corpus. And then in the English, it's not 90,000, it's 83,000, because actually some of those units that occurred in the German haven't been seen in the English. But when we require that we see the subword units in both source and target by some minimum threshold, the vocabulary size drops from 83,000 in the English to 52,000, and in the German from 91,000 to 73,000. And that makes quite a significant difference in the size of our models. We were hoping it might make some change to the blur score. It didn't seem to affect that really at all, and also didn't make the sequences any longer. Another way that we tried to make our model smaller, this year there was a paper by Press and Wolf which proposed tying weights of the embedding matrix and the transpose of the output matrix together. So these matrices are the same size, and in fact, when you force them to be equivalent, you get smaller models, and it seems to have no impact on the quality of your translations. So we applied this. And then we were looking at making our training faster. So last year we were using Ada Delta as our optimizer. And this year we were trying to, we followed Kingman Bar, and we applied the Adam optimizer instead. So the Adam optimizer is basically Ada Delta with encoding this idea of momentum. And it seems that we've noticed that training converged faster, and we were getting better results with it as well. We haven't yet trained our systems with Adam with annealing, but this is already implemented in Nematis, and we'll be doing experiments on it in the future. The other thing that we implemented in Nematis, and we've tested in this paper, is adding layer normalization. So Barr and Hinton proposed layer normalization because learning is actually complicated in deep neural networks by the fact that when the parameters of your input layer change in training, it changes the distribution of the input that you get in the current layer. And that slows down training. It makes it harder for the model to learn and slower. And so if you normalize the inputs, then you can recenter it and rescale these, and it makes learning easier and makes the models converge faster. And so we implemented this, and we tested this in the system paper. So probably the biggest contribution that we've made this year is we actually have a paper on deeper models in neural machine translation, and we have another paper in WMT on that. But we didn't have the chance in that paper to test it on many different language pairs, so the shared task was the perfect chance to see if this work still applied, still had good results across many different language pairs. So we implemented, we tested in this paper, we tested 2 different kinds of deeper models. The first deeper model we call stacked RNNs. So we took inspiration from a paper written last year by Zhao et al. From Baidu. And their model proposed using alternating stack encoders. So here the idea is that you have RNN models trained in different directions. So left to right models are here represented as blue, and right to left models are represented here in brown. And then you stack them in alternating directions, and then the final step is you take the context from the first time step, and you concatenate the forward and the backward stacks together, and then use that as input to the attention model. The Google paper, also there was a Google paper which proposed a deep model, which we explored in the paper that we have on deeper models, but it didn't seem to work as well. We also proposed using deep transition networks in machine translation. So these have been proposed in other places, but this is the first time they've been applied to neural machine translation. And the idea here is that you can actually, within the recurrent cell of the RNN, you could have layers. You could have a feed-forward network within the recurrent cell. And the advantage of doing it this way is that there are far fewer parameters in this model than the previous slide, because you don't have parameters going left and right. You only have parameters going up. So you could say, well, the path becomes very long. But actually, we show that this model is quite fast and shows quite good results. So in all of these submissions, we used a depth of 4 layers. And the other thing to note is that with our implementations of these deeper models, certainly like for Google paper, they said that the results that they got were from training on a cluster of 96 GPUs over a period of 3 weeks. And that means that their results and their research aren't really relevant for the majority of academics or mere mortals. But what I think is really noteworthy about our work is that, in fact, all of these models were trained on one single GPU. Admittedly, they took a bit longer to train. So in the smorgasbord of features for neural machine translation, not features, research, it's very important to mention the ability, the need to use monolingual data in training neural machine translation models. So another of the drawbacks of neural machine translation previously was that you would train them on parallel data, but there was no obvious way of using monolingual data in the target language to train up your models. And then last year we proposed a method of using synthetic data or back translation. So you back translate with a machine translation model trained in the opposite direction to the one you're interested in. So you have good quality translated text, and then kind of maybe slightly poorer source language text. But what the real reason to do this is that then, because monolingual data is so much more freely available than parallel data, you can either get vast quantities of it, or you can, even more interestingly, get data which is perfectly in domain for your particular use case. So if you're translating into, so we have some experiments on the biomedical task, for instance, you're not interested in using Europal. You're wanting to have text which is about medical health, about public health, and then if you can collect this data relatively easily on the web, and then you can perform data selection, which is very important for producing good quality systems. We used Moeller's data selection to be able to label sentences with how in domain we consider them to be. So we train up a language model on our in domain biomedical text data, and then we use that to label general domain sentences as either in or out of domain. And then we back translate all that data into the source language. An interesting thing we tried, which was something might be of interest if you had very little parallel data, and even back translation won't help you because the quality of the systems are pretty poor, is adding just monolingual data. So if you're translating Turkish to English, for instance, and you've only got 200,000 sentences of parallel data, you just copy the English into the target and source of your parallel corpus and you train on, mixture of Turkish and English on the source and English on the target, and it seems to help a little bit. So finally, we performed ensembling and re-ranking. These are techniques that are certainly not novel, and last year we used ensembles which were checkpoints. So instead of training up independent models, we just saved the model at different time steps, and then we ensembled those, and that worked. And this year we contrast that with doing what is probably the preferable thing, which is training up for independent runs. And then finally, we perform re-ranking with right-to-left models. So neural machine translation models make mistakes. Sometimes they start producing really crazy sequences of words like, no, 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 or something. And they seem to, once they get into a sequence in the target language that's very unusual, particular, they seem to lose information coming from the source language and get stuck. So if you translate from left to right and you create n-best lists, and then you take a right-to-left model and you re-rank these n-best lists with a right-to-left model, you have models that certainly both could make mistakes, but you hope that they don't make the same mistakes. So very briefly, this is an overview of our results from 6 languages into English. And I'll just discuss them in a little bit more detail. So for the systems, we had 3 systems that we submitted to last year's WMT. And out of interest, we ran them again on this year's data. And we saw that even our baseline models from this year are better, stronger than our last year's models. And this is due to the fact that we're now using back-translated data for all these language pairs. Adam and the new BP strategy is helping as well, potentially. And then we added layer normalization, and then on top of that we added deep models. So unfortunately, some languages used the recurrent deep models, and others used the stacked deep models. But you can see consistently that both of these things help. So for layer normalization, we're seeing improvements of, between nearly 1 blur and half a blur. We see less for German to English and Latvian to English. Sorry, German to English we see very little gain, but quite consistent for the other languages. And then for deeper models, we see again another improvement of about, say, between 0.7 or 1 blur point improvement. For the Latvian to English, it didn't seem to help. Maybe we didn't have enough data, or maybe Latvian is just a very difficult language. But for all of the other languages, we see consistent improvements. And then taking our single model now as the baseline and seeing what difference the different kinds of ensembling makes. We can see again here that we're confirming that checkpoint ensembling really helps, but independent ensembles are always better, and sometimes quite a lot better. So for Chinese to English, instead of 23.6, we have 25.1, so that's a full blur score and a half difference. And then again, re-ranking right to left also helps more. We saw more gain last year from right to left re-ranking, and probably last year our baseline models were weaker. So as your baselines get better, other things on top of them tend to help less. So stepping back a bit, looking at all of the results together, although all of the things we've tried have and we did actually try quite a lot of other things as well, which didn't work. All of these things consistently improve over the baseline, and we're able to actually improve overall quite considerably. So, you know, between 4 and 5 blur points over our baseline. So, you know, all that effort, I think, paid off. Also, you can note that sometimes our system submissions weren't quite as strong as our final models due to pre-processing mistakes, and so that's what happens, unfortunately. And then I won't go into any detail, but out of English, all of the results that I have previously mentioned still hold. And we performed a similar set of experiments for the biomedical task, and we have similar results there too. And here are the results that show that for very small amounts of training parallel corpus, if you just add the monolingual data in both the source and target, you can see an improvement. So for English to Turkish, you get nearly a blur point improvement for that, which is quite surprising. And in this slide, I just want to highlight that if you do domain adaptation, if you take, you do data selection for your monolingual, the monolingual data that you then back translate, and then you train with it, you can really improve systems enormously. So here we can see, we didn't do these experiments for the news task because we knew this worked, so we just simplified our lives by just doing it straight off the bat. But we can see here, you know, for single models, it improves the blur score by 4.5 blur points, so from 22.8 to 27.2. And for ensembles, it still improves by nearly 3 blur points. So you clearly want to do that if you want to win WMT shared task. So because I'm trying to motivate shared tasks and encouraging you to submit your system papers to shared tasks, I'll just put up here a glimpse of the, these are not yet available, so so I don't want to discuss them in too much detail, but just to get an idea of what the shared task involved is that another really good thing about the WMT shared task is that it's all very well to use blur scores to evaluate our methods, but actually it's really important to have conclusive evidence to use human evaluation. So these are the results for English to German, German to English, where humans have evaluated the output of machine translation systems using this method called direct assessment, where they're asked to give a score between 0 and 100 of how good the translation is, and then using standard statistical techniques, the scores are normalized, and you get an overall score for a system, and that's the average Z that you see here in the table. So just briefly, obviously our system is doing quite well. So the systems are ranked, and then if we're able to distinguish clusters of systems that are significantly better, the whole cluster, every system in the cluster is better than every system in the cluster below it, then a black line is drawn. So in fact, you have a lot of tied places. So in English to German, there's a first place system submitted by LMU. And then in the second cluster, we have maybe 8 systems, which are all tied second place. So I think it's interesting because our system got a higher blur score, for instance, than LMU. We got 1.2 blur scores higher than they did in the automatic scoring. But then what falls out from this is that, in fact, humans really did prefer LMU system. So it was a good system. It had good blur scores, but they did morphologically motivated segmentation on the German side of the corpus, on the target side of the corpus, and humans seem to really like that. And that result would have been missed if we hadn't done, if we hadn't had a shared task where everybody had the same training data, like for like, and we used humans to evaluate. So I think that that we can see the real value in shared tasks coming out of results like this. In the English to Czech results, so in English to German, there's not that much. There's relatively less amount of training data. There's about 5 million sentence pairs. And in English to Czech, there's a much bigger corpus, the Czech corpus, which is about 50 million sentences. And I think what's interesting is that our favorite commercial translation provider, Online B, we've always been beating them actually in English to German over the years, and then we can see here that now they're beating us, right? Which is very good for them. But as you can see, they're in gray because they're unconstrained. So they used who knows what training data, but it's almost certainly an order of magnitude larger than the training data that we're using, which is the ones provided by the WMT shared task. So still don't feel too bad about that. But then if we have access to a large amount of good quality parallel training data, that our models seem to still be preferred by humans in the English to Czech language pair. That might be a feature of Czech, I'm not entirely sure, but it's interesting anyway. And I think I'm going to leave it at that. Thank you very much.
Questions?
Thank you for the talk. I have 2 questions. The first one, it's about the pre-processing steps before, of course, training the neural network. Did you do more than tokenization, like Moses, for example?
So it's very basic pre-processing. I mean, literally, we normalize it for UTF-8 so that commas are always the same character, and then we remove very, very long and very, very short sentences, and we tokenize and true case. Those are the things we do, and yeah, it's very compared to Moses, where the training pipeline was incredibly long and involved. It's now very quick and very simple.
Okay, thank you. The second question is about domain adaptation. I didn't understand exactly how you deal with this. Did you just add bilingual text on domain, or how
Yes.
do you deal with it? Yeah.
So what's really difficult is to find in-domain parallel training data. Previously, the tuning step of Moses required very few, like 1,000 sentences or something that might be in domain. So you'd have a tuning set of, a small set of, because you were really just tuning these 10 weights or something of the 10 features that Moses had. But with neural models, there's no features, there's no weights. And they actually are incredibly greedy. They require large amounts of training data. So 1,000 sentences would be a joke. I mean, there is work on how to do domain adaptation with very small amounts of training data, but it's very difficult. And if you have in-domain monolingual data, what seems to work really well is back translating that. And then adding that into the parallel training data, kind of at a ratio of 1 to 1. So like if you had 100,000 parallel sentences from your human translated corpora, and you add another 100,000 of back translated data, you mix it together, shuffle, and it works.
Okay, thank you.
Hi, thanks for a great talk. Lots of really interesting developments, and it was a fantastic way to catch up on a field I haven't really worked in for a number of years. I have one kind of high-level, hopefully easy question, and you may have already answered it, so sorry if you did. When you're training the neural net, like the big end-to-end system, at the very top there's a loss function. And I'm curious whether there's any, I want you to remind me what you used, and I want you to tell me if you know whether there's much variation there, or is everybody kind of doing the same thing? Is there any, I mean, MERT's gone, right? We're not using MERT anymore to optimize the parameters of our MT systems. It's now all end-to-end, which seems like the right thing to do from a machine learning perspective, but what's the loss?
We're trying to optimize entropy.
It's cross-entropy.
Yeah.
It's the log loss. So has anyone tried to bake something like the blue score, or the inverse of the blue score, or 1 minus the blue score, or something into the top level objective function?
There is work on this, yes.
Does it work?
There was a paper last year, which I think it was called minimum risk training.
Sure.
So the idea is you do your standard training to convergence, and then you start producing n-best lists.
Right.
And then scoring those using Blur,
Okay.
or any other metric.
So it's like end to end, and then end to end again, with a little bit of different stuff happening at the end, because this is kind of hard to calculate and expensive and so on.
Yes,
but
and we reproduced it, and it didn't work.
Oh,
so
not promising.
So that's why shared tasks. If it worked, it would be there.
Okay, thanks.
And it might still, maybe we didn't get it right, maybe.
Sure. Maybe you needed a bigger at-best list.
Hi, thanks for a great talk. You mentioned that Google, in their papers, mentioned that they trained for 8 days on 64 GPUs. I think you mentioned here that you use single GPUs for training your models, but still you burned like €30,000 doing these experiments. So I wonder, like, if you're not Google and you're also not in University of Edinburgh, like maybe some of us here are lucky if we have 1 GPU available, right? So can you, basically, what do you need to do in order to make your improvement over neural machine translation, like your feature that you come up with, that makes it better, to make that believable? So what kind of baseline?
I mean, you have to see, what are my resources? And then you do the very best. I mean, in a way, that was what I was hoping. I didn't want to just present a system description here. I wanted to motivate you to be very thorough. But of course, there's real-life constraints, and the resources are finite. And but you know, things like checkpoint ensembling doesn't cost you any extra. And you absolutely have to do at least 2 language pairs. You know, anything on 1 language pair, I would be skeptical of. So there's some things that you really need to address, I think. And do as best you can. And if you have an interesting idea, you know, maybe somebody will try to reproduce it. But to get to that point, actually, it should be as convincing as possible. Otherwise, you know, people will go like, oh, you know, don't believe it. It's difficult. We're all struggling with that. But I think this is something that this kind of paper could be like an example of what you should try to do. But it's not going to be practical most of the time.
All right, thanks.
And just following this question, actually, I would like to ask whether, what do you think we try to, because I mean, most of the group may not access to these hundreds of GPUs, right? So whether it's possible that we use a cluster of CPU to replace it. Actually, I mean, I think a lot of our group may have more than 100 cores of CPU. So if we have enough number of CPU, whether do you think it's doable to do the training of a large scale of deep neural network?
No. No, you need GPUs. But
actually our work this year, actually we use CPU with
oh wow.
Yeah.
Okay, sorry.
But maybe in different domains, so we are actually kind of in small scale, so in different domains. So my question is whether you try to use CPU in the machine translation.
So we've put a lot of effort into CPUs for decoding, for actually kind of production-ready translation for customers and clients, because CPUs are just so much more available. So it's, and I mean, we have a very large cluster of CPU machines which are standing idle at the moment. I actually don't even, I know, yeah, we've tried to train on CPUs, and I can't remember how slow it was, but it was incredibly slow, and it just, I don't know theoretically if there's some way of calculating it, but yeah, I think you should use GPUs for training.
Hey, thanks for your talk. A quick question about two techniques. First, you said you use layer norm. I found in my own experiments that layer norm in TensorFlow, at least TensorFlow 1.0, runs about 10 times slower on an LSTM, and this is on a GTX 980M graphics card. So, did you find
So we found that the epochs went by slower, but the convergence was much quicker.
So you reach convergence much faster. Okay. The second one is, have you considered trying to use NCE? So I mean, you still have your softmax at the end, which is an expensive operation. And NCE, this noise contrastive estimation, is a technique which can allow you to sort of do a softmax without having to do the normalization. And we found in our experiments with language modeling that we can get very, very large training time speed-ups with very minor drops in perplexity. Have you considered using this? Or? We
have looked at it. Off the top of my head, I can't remember exactly how that ended up. It's an interesting technique, and I would very much like to see any paper you publish on it.
So it wasn't my work, it was somebody else from our lab at Cambridge. Okay.
But confirming, reproducing,
sure.
which I argue is very important and valuable.
Mm-hmm. Thanks.
In regarding the tied embeddings feature, did these models use that? The ones that you submit to the shared task?
Yes.
Okay.
Yes, so in order to train a deep model on a single GPU, we needed to make the model smaller. So that was one of the first things we tried. And it allowed us to do all this, the work on the deeper models. So it was quite successful, I think.
Thank you.
Thank you. I have another question. It's about, in the case of Moses, for example, we tried to add some morphological information and also part of speech tagging to improve the translation quality. I'm thinking particularly on factorial models. Do you think it's possible to do that with neural machine translation?
It is, and it helps. So last year, my collaborators, Barry and Rico, have a paper at ACL where they used pos tags and dependency labels and other features, linguistic features, and they had embeddings for the features, and they concatenated the embeddings of those with the words on the source side, and that seemed to help machine translation by a small amount. It's maybe slightly at a tangent to maybe the standard kind of neural network research where everything is the model, and it's kind of heretical to add, hand-programmed features in. But it actually, across a number of different language pairs, shows to help. So you could look at that if you're, if you have a language like Latvian or something that's incredibly rich, it might be worth trying to do that to improve translation quality.
And do you have an idea about the blue score or the improvement you have comparing to Moses, for example? Because in your figures, maybe the baseline is not Moses, is a neural machine.
Yes.
Do you have an idea about?
We did this last year.
Yeah. Okay.
But our resources were already very stretched, so it is possible that for one of these 12 language pairs, Moses might beat us. Certainly something like Turkish English, you know, 200,000 sentences is very little. I wouldn't be surprised if Moses did better on that. You need, you know, if you have 1 million or 5 million better or 50 million even better, yeah, for training the neural models.
Okay.
But it had to be useful to our research too, and to be honest, none of us are now working on phrase-based machine translation, so it didn't seem that valuable for us.
Okay, thank you.
Thanks for your talk. I have one question regarding ensemble for models. Regarding ensemble, did you train 4 different architectures, or you just trained 4 times, or maybe with different random seeds? And because I just saw if you run just the same model with the same random seeds 4 times, ensembling helps.
Yes.
Just I want to know.
Although you have to start with different seeds.
No, even with the same initialization.
Same seeds. Okay.
Yeah.
Well, if you shuffle your data differently, if you have the same seed and the same shuffle data, you wouldn't get much out of your independent ensembles. They wouldn't be very independent. I've not tried that, but I can't imagine it would be a good thing.
Thanks for your talk. I'm curious how the training time for this year's submission compares to last year for language pairs like English German or English to Czech.
Say that again, sorry?
How the training time compares with respect to last year.
We didn't actually record that. We didn't record the time to convergence. The layer normalization made it converge faster, but then the deeper models made it converge slower again. So I think we ended up between training times between a week and up to 2.5 weeks for the models. I don't know how that compares to last year. It seems to be maybe similar overall.
But we better about that? Okay, thanks.
Okay.
Thank you for the talk. I participated in this year's share task and also the human evaluation. I found for Chinese and English language pair, there's many mistakes caused by word ambiguity. So what about other language pairs, and what do you think of neural machine translation and word disambiguation?
So, I mean, ambiguity is one of the great challenges in natural language processing. And I'm not surprised, actually, that we're failing on that. But thank you. It's interesting to hear from a Chinese speaker. It is difficult when your vocabulary, you know, you could have an item in your vocabulary that has very different meanings, and it's sharing and embedding. You know, I guess the embedding would encode some of the context of both of those different meanings. And of course, you could also use extra linguistic information, like I was mentioning previously, to have like a word sense disambiguation label on it as added information, and that could maybe really help. So maybe that's something that we should try for Chinese.
Okay, thank you.
One more question about the architecture and the deeper models that you were talking about. So you showed that you used four layers. Is that right? On all language pairs, or do you make a difference between some language pairs you did the deep transition RNNs and some you use the stacked RNNs, or how do you pick between the two?
So it would have been good to use one architecture for all the language pairs, but because different researchers were interested in different things, we applied them. If you read the paper, that describes which model was used for which language pair. But there were 4 layers for each. Obviously, a layer means something different in those two models, but you know, that's how we parameterized it. So you know, we didn't do, like, for instance, Latvian didn't have that great results with the deep models. Maybe 4 layers was too much for Latvian, or maybe it wasn't enough. I'm not really sure. We did a more of an exploration of the deeper layers in the paper on deeper models in WMT, in the research paper. So there you can see a comparison for English German on the different architectures.
Okay.
So I'm just curious. So compared with the system from last year, did you notice that the translations were mostly more fluent, or did you observe also significant improvements in adequacy? So did you observe fewer critical errors?
That's a very difficult question to answer. There were still some critical errors, but they're actually not that frequent. So you'll notice them because when they're wrong, they're obviously wrong. But it tends to be just 1 in a few hundred or 1 in 1,000. But even last year, they weren't that frequent, really. Those completely garbled sentences.
So thanks for the talk. So do you have an intuition of what's being the actual bottleneck on these models? So would you say that it's on the encoding side, or it's on the decoding side in a certain way? And like a related question is, would training a system like this in a multitask scenario help? So for example, you would both produce the translation and replicate the input based on some common representation. Would this help?
I think that's a fascinating line of research. We have been experimenting with reconstruction, so adding to the loss function some idea of the score and the back translation. So how good is the model in not only producing the translation but also producing the source? And we haven't seen any real blur score improvements there, but I think that absolutely needs human evaluation because you'd imagine that the adequacy there would be much better, but maybe the fluency, the blur score isn't affected. So that's why human evaluation really is essential in machine translation research. So it's a very interesting idea. I'm sure there's many ways of doing it as well. The one we've tried, we tried to reproduce some previous work. So it's ongoing research. I'm hoping it'll work.
Okay, guys, so let's thank the speaker again. And well.